So what we are going to learn today is something called linear modeling. Now, when we talk about linear modeling in general, we know that when we create a scatter plot between explanatory variable EV, which happens to be my X, and my response variable, which happens to be my Y, whenever I'm creating a graph, a scatter plot, not the graph, I mean, I can get something like this. If I ask you, what is this scatter plot? Can you define the scatter plot? So you can say it is a linear because it looks like a straight line, linear, positive, strong association, right? And if I were to ask you to guess the value of R, and if I were to guess it, I'll say maybe a plus 0.80 R value. I'm just guessing it, right? Now, what we're going to do today is that, for example, let's say this EV was the height and RV is the weight of a person. Height drives the weight. More the height, more the weight. More the height, more the weight. Less the height, less the weight. Right? So let's say I have experimented on some 10, 15 adults. And let's say it starts at 45, 50, 55, 60, 65, 70, maybe 75. And let's say, no, sorry. I've written so this is height. So let's say height is 120 centimeters, 130 centimeters, 140 centimeters, 150 centimeters, 160 centimeters, 170 centimeters, and 180 centimeters. This is my X, the EV. And let's say my weight is, if I just take this off, and I say this is, let's say, 50 kilos, 60 kilos, 70 kilos, 80 kilos, 90 kilos, and maybe say 100 kilos. This is in kilograms, and this is in centimeters. Okay, I got this scatter plot, and I just have randomly, experimented a few adults. Now, if I ask you that, tell me how much is the weight of a person who is weighing, whose height is 120 centimeters. So what you can do is you'll say, okay, let me just quickly check your scatter plot. That do you have any particular dot in your scatter plot corresponding to height equals to 120? So hang on, yes, I've got one. So that means I have experimented someone with the height equals to 120 and the weight was 50. So I'll say the weight is 50 kilograms. I've actually experimented it, and the proof is that I got the dot on the scatter plot for the height that I'm looking for. Cool, this was fine. Now, I now ask you that, tell me whether you have the weight of the person with height equals to 130 centimeters. And I'll say, hang on, let me check whether I have experimented that that person with 130 centimeters was there in my experiment or not. Let me quickly check. Oh, yes, I had one. And I happened to be, the weight of this person was uh, 65 kilograms. Cool. Now I ask you, okay, can you tell me if you have someone with the height 150 centimeters and can you tell me the weight? And I'll say, hang on, let me check. So for 150, sorry, I don't have any weight for the person with the height 150 centimeters. I did not find any person with that height when I was collecting my data. So I missed it. So in this scenario where I have collected the data from someone who was measuring 120 centimeters and I've actually gone up till 170 centimeters, I found the weights of all of them, but I still missed someone weighing 150 centimeters. So how do I find the weight of this person who is 150 centimeters without going back and doing an experiment and trying to find this person with 150 centimeters? How do I do it? The way I do it is something called linear modeling. What is the linear model? The linear model says that I will now draw a line, and hear me out loud and clear, and I'll draw a line. Probably I'll change the color of my pen. Let's say I take a green. I will draw a line bang in the middle of my scatter plot. And I call this line as least square regression line. This line will now help me to predict the weight of any height between 150 to 170 centimeters, even if that person was not in my experiment. Are you guys getting it or not? What I'm just saying? Yes or no? I need to see a nod. Yes or no? Right? Cool. Now, let's try to find the weight of the person with 150 centimeters of height, because this person was not there in my experiment. So I'll go to this person again and I'll draw the line. I'll see where this 150 centimeter is hitting my least square regression line. And I will use its corresponding y value. So which happens to be, if I have to guess, it's 82 in this particular case. So least square regression line helped me to predict that the person with the height of 150 centimeters is having a weight of 82 kilograms. Does that make sense? What is the use of least square regression line? It helps me to predict the response variable based on the values of my explanatory variable. Even if the explanatory variable was not there, the data corresponding to that explanatory variable was not there in my original experiment. Making sense now? Yes, no? Cool. All right. Now, let's go to the next page. So if I draw the line again, so I had this kind of a scatter plot, just randomly drawing it again. This was my height. Probably I'll write it lambda. This is my height. That's my weight. And I've drawn a least square regression line bang in the middle. And I was able to predict the weight of the person whose height was 150 to be 82 kilograms. Now, understand this. We'll take this concept a step ahead. The green line is a straight line. Yes, a linear straight line. For a linear straight line, how do we write a linear straight line? We write it as y equals to mx plus c. Do you remember that from your grade 10 days, the slope-intercept form, y equals to mx plus c? We don't write it like that here. In the world of data, we write it slightly differently. We'll say y equals to a plus bx. One, we write it the other way around. This c is the y-intercept, if you remember. Similarly, this a is also the y-intercept of this line. M was the slope. Similarly, B is the slope of this line. So now I will not write y equals to mx plus c at all. I'm taking that off now. Rather, I will just use y equals to a plus bx, where a is the y-intercept. Let's see what is y-intercept in this scenario. If I just extend this line a bit, that point is the y-intercept, the point where the line hits the y-axis. And what is A? A is the slope. What is the definition of slope? Slope tells me rise over run. Yes? And what is rise over run? Change in y over change in x. And what is y? Change in the response variable over change in the explanatory variable. So the definition of A is the change in response variable per unit change in the explanatory variable, or my x value. So far, so good. I hope you're not lost. You're not feeling sleepy. It's too much going in, right? Oh, good. I need to see a nod, right? Cool. Thank you. Now, let's jump on to another concept, which is like the last concept in this linear modeling. And I'll take another page here, and I will draw the linear graph again, the scatter plot again. So my scatter plot was and I draw my least square regression line here. Now, let us say this, I'll probably change the color. This value is 140 centimeters height. And let's say this value is maybe 60 kilos. And then maybe this is 70 kilos. Now, if I ask you what is the height of, so what is the weight of someone whose height is 140? So you can go here and say, hang on, here. I have actually a person in my experiment with the height of 140 and the weight is 60 kilos. So you'll say for 140 centimeters, the weight is 60 kilograms. This reading is called the actual reading. The actual reading. But then I told you that the least square regression line, this green line, helps us to predict as well. So what is the predicted value for this person who's got height of 140 centimeters? So I'll go here. I'll say, okay, let me see where this is hitting the line, my least square regression line. Hang on. The prediction tells me that it should be 70 kilograms. So the actual value, I'll say A, is 60 kilograms, whereas my predicted value for the same value of my X component or my EV is 70 kilograms. And now I see there is a difference. That is the difference. This difference is called residual or the residual value. How much is the residual value here? So the formula to calculate the residual is actual value minus the predicted value. My actual value is 60. My predicted value is 70. So negative 10 is the residual value for the height equals to 140 centimeters. Is this clear? Any doubts so far? Anyone? Any doubts? No? All right. Now, last observation. This value, the actual, when your actual value is sitting under the least square regression line, your residual values are always negative. Now, let's take another example. So let's say I have this value here, which is let's say I'm just making something up, 170 centimeters. And I'll tell you, and I ask you, what is the actual value at 170? So you can just say, okay, there is a dot here, must be 100 kilos. So the actual value for 170, the actual value is 100 kilos. But what is the predicted value? You see here, here is the predicted value. That's the dot where it's sitting on the line. And if I just say this must be, let's say, 90. So the predicted value is 90. So what is the residual at 170? Residual is actual takeaway, predicted actual is 100. take away predicted, which is plus 10. So to sum it up, when your residual value is a positive value, it simply means that your actual data is greater than predicted data, and your dot sits above the least square regression line. And when your residual is negative, it means your actual data is less than your predicted data, and hence your dot in the scatter will sit under the least square regression. Is the concept of linear modeling clear so far? So what we learned? We learned that there is a scatter plot and I can draw a least square regression line. The least square regression line looks like a plus bx. A is my y-intercept. B is my slope. Sorry, this is B, my bad. This is B. B is my slope, not A. And there's something called residuals. So if my residual value is a positive value, that means my data is sitting above the line. If my residual is negative, my data is sitting under the. All good? Clear? All right? All good.